Hello, everyone, and welcome to another wonderful day of chemistry. Last time we covered coordination compounds, what they are and kind of what they do. However, because it's chemistry, we have to know how to talk about them. And for that, we need our own special language, nomenclature. So whenever we're looking at these coordination compounds, most of these are going to occur as ionic complexes. So they're going to have an overall ionic name. So we're going to go ahead and try and use a general set of systematic names to be very consistent so you know what we're talking about. So they're going to follow a same general format where we're going to name all of the ligands attached to our metal, and then we're going to make sure to name it as an ion to let you know we have an overall charge. So most of these rules focus on how to name our ligands, and there's a lot of them. So let's go ahead and look at those first. So the first set of rules is if I've got a neutral ligand, then I'm just going to use its unmodified name. So good examples are going to be nitrogen-rich compounds like amine and pyridine. However, watch out, there's a lot of common molecules that have their own special names. For example, if you have something like water, it's just named as aqua because we have to keep things fun. And some of these were actually named before the common systematic names. So we've tried to incorporate them in. Now let's go ahead and take a look at some of our anions. So one of the most common types of sets of anions have the "ide" ending. So for example, if I have something like chloride, oxide, or cyanide, we end up replacing those with ido endings. So chloride becomes chlorido, oxide becomes oxido, and cyanide becomes cyanido. So again, one of the things to watch out for is there was an older set of nomenclature which replaced the ides with just O's. So you often had chloro, oxo, and cyano. So watch out for those if you're looking at older nomenclature, but for the last 15 years, we've used this newer set. Now, the other thing you may wonder is why do I have to use a different suffix instead of the classic ides? Well, one of the big reasons is you often have a lot of chloride or cyanide going around in solution. So you have to make sure that it's not just a counterion, but it's actually bound to the metal. So to make sure it's very explicit that it is a ligand, we give the ligands their own special versions of these names. So it's something to keep an eye out for. Similarly, we have a lot of anions that end with "ite", so nitrite and sulfite. We replace that E at the end with an O, so nitrite becomes nitrito, and sulfite becomes sulfido. Similarly, with anions that end in an "ate", so things like sulfate and nitrate, those end up going to sulfato and nitrato, where again, we replace that last E with an O. But most of the general rules tend to work out like that. Now, the next thing you have to watch out for is that all of these ligands are nice monodentate systems, which means we're going to have more than one ligand attached. So if I've got more than one of the same ligand, we often denote how many with a prefix. So specifically, if we have 2, it becomes di, then tri for 3, tetra for 4, penta for 5, and hexa for 6. So if I have an amine ligand, 1 would be monoamine, more commonly just amine. 2 would be diamine, then triamine, then tetramine, then pentamine, and then hexamine. However, one of the things we have to watch out for is if the ligand already has di in its name. So for example, think about ethylene diamine. It would be weird to say I've got 2 ethylene diamines, as in diethylene diamine. That's just confusing. So if the ligand already contains di in its name, we're going to use bis and tris as prefixes. So it would become bis-ethylene diamine and tris-ethylene diamine. So one of those things to watch out for. Finally, if I've got more than one different type of ligand, I'm going to name them according to alphabetical order. So amine before bromo, before chloro, before oxo. And this won't depend on how many of each there is. So we're going to ignore any prefixes and base it just on the ligand name. So that's how we cover the ligands. Now, how do I name the metals? So if my overall ligand complex is coordination complex is positively charged, I'm just going to name it according to the metal and its oxidation state. Because again, I don't no longer know the overall charge of the whole ion. I need to make sure that I know how the positive charge of the metal, and then I can figure out the rest of the charge based on what ligands are bound to it. So for example, cobalt is most commonly found in the +3 oxidation state, but I need to be sure because you can occasionally do some fun stuff to it. Now let's say that the entire complex is going to be negatively charged. I need some way to know that my complex has a negative charge, not a positive charge, because this will affect how it interacts with its surroundings. So in that case, because the metal goes last, I'm going to attach an 8 ending to the metal. So it goes from cobalt 3 to cobaltate 3, which starts sounding like a hero. So let's go ahead and take all of these general rules and put them into practice. So again, here's a list of some of the more common monodentate ligands. Again, some of the odd ones to watch out for are aqua for water and nitrogen for nitrogen oxide, and things like with nitrito and can either coordinate through a nitrogen or an oxygen. To know who's bound to the metal, we just denote that with its own letter. So let's go ahead and dive in with this nice chromium complex. So first, let's take a look at the ligands. We've got amine and we've got bromine. So amine will go first as it starts with an A. So I've got tetraamine and then dibromido, finishing with chromine, which let's try and figure out what the oxidation state of this chromine is. We have an overall +1 charge, and we've got -2 charge coming from that bromine. So that means that my chromine has to be a +3 charge for everybody to work out. So this would be tetramine dibromido chromium 3 ion. Now let's have fun and go to an anionic iron complex. So let's go ahead and take a look at our two ligands. So we've got cyanide, which becomes cyanido. And this one gets fun because our nitrogen oxide becomes oxidonitrogen. Now this one will become second because it starts with an O. So we start with pentacyanide, cyanido, oxidonitrogen. Yes, that's a little bit long. Now we have to go to our iron complex. What's going to be the oxidation state here? Our nitrogen oxide has no charge. Cyanide has a -1 charge, but I've got 5 of them, which brings a total to -5. I need to cancel out 3 of those charges to get an overall -2. So I've got a iron 3 complex, but we've got an anionic system. So it goes from iron to ironate 3. So putting it all together, it's pentacyanide, oxidonitrogen, ironate 3 ion. Whew, that's a mouthful. Now let's go ahead and look at a fun cobalt compound. So here we've got chlorine and ethylene diamine. So chlorine will go first. So it'll be dichlorido, but now we have to watch out because it'll be bis-ethylene diamine, cobalt, again, 2 negatively charged ligands and an overall plus charge means we're cobalt 3. So dichloro, bis-ethylene diamine, cobalt 3 ion. So these names get a little bit long, but to make life even more fun, a lot of these species won't actually occur as free ions. I'm going to often add them to water as salts. So in this case, instead of having a positive charge on my chromium complex and having it floating free, that positive charge will be counteracted by a single bromine. Now, whenever we're naming these species, we're going to keep the ionic name generally the same. We're now just going to drop ion from the name, and we're always going to name our cation first. So in this case, my complex ion is going to be the cation. So I'll name it first, tetraamine dibromido chromium 3 bromide. This way I can get the charge from here, and then I have a single bromine to cancel it out. Now for the potassium complex, potassium is the cation, so it goes first. Then we go ahead and name the system. Pentacyanide, oxidonitrogen ironate 3. Again, with the 8 denoting that this is going to be my anion, while potassium is going to be my cation. Now to finish up, we've got dichlorobisethylene diamine cobalt 3 chloride. So bringing it all together, we should be able to both name coordination compounds based on their structures, and if we get the name, be able to interpret what we're looking at. So next time, we're going to go ahead and look at the multiple different ways we can bind these ligands to a single metal center. Till then, take care.